Hi, I'm Anna.
I'm Benlin.
I'm Alexia.
And this
is
Q Learning with Celeste.
A quick overview of the introduction, methods, results, discussion, and conclusion. Celeste is a complex timing-specific video game that requires long horizon planning and precise execution. This project evaluates the effectiveness of different Q learning models to learn policies to progress through the rooms.
Some relevant prior work includes Mario, a neural network-driven agent that learns to play Super Mario World using NEAT, an evolutionary algorithm that evolves both network weights and architectures over time. This approach shows that machines can learn platforming behavior without being explicitly programmed. However, Mario relies on huge numbers of trials, repeatedly spawning and memorizing actions at each step. Our goal with Celeste is to learn more efficiently, making better decisions from fewer attempts based on what has already been explored.
So we wanted to write our decision-making algorithms in Python. However, Celeste is written in C#, so we wrote a custom mod to transfer state to and from the game using shared memory. And basically, from Python's perspective, the entirety of the game's code was abstracted away as the simulator of our MDP, and Python just pretended it was talking to some MDP interface.
For all three methods, the reward is a function of the change in XY positions, favoring movement towards the upper right corner. A slight boost is added for climbing upwards and for each new highest platform reached.
For the tabular Q learning approach, we define a game state using the combination of following 7 features and our action space using 128 combinations of the 7 movement inputs. We build a Q table over state action pairs and update it using the Benlin equation at each step. The main drawback is speed. Tabular Q learning updates only one state action pair at a time, making training slow.
Functional approximation maintains an array of weights to be multiplied with features for the Q values. This represents an improvement upon tabular Q learning in that it updates weights for a given action for all states, rather than a given state action pair. This means that patterns learned for a given state may be generalized to unseen states, unlike the memorization approach of tabular Q learning.
So the final method we tried was DQN, which is basically function approximation Q learning, except we use a larger network, deeper network, and we add various tricks that make the training more stable. Right, so right now you're about to see our system in action. We're showing you seed 4 of the function approximation Q learning algorithm, which is one of the best runs we had. Right now you're seeing us speed up the game to 20 times speed. During training, we used 99 times speed, which was important just to tune all the hyperparameters and make sure that things could get done in a reasonable amount of time. The way speed up works is that we call the game's inbuilt update function multiple times per frame. So we're basically skipping over the rendering of certain frames, which is important since Celeste runs at 60 FPS. And as you can see, here we get to the 4th room of the game.
Below are the numeric results of our training. The graph shows the average percentage of rooms cleared over 1,000 depths, tested across 25 random seeds. At the very beginning, fully random actions actually perform the best, since the learning-based methods haven't yet adapted. Over time, the other 3 approaches start to improve, but at different rates. Tabular Q learning lags behind early on due to slow learning speed, while functional approximation steadily outperforms it. Our DQN approach shows potential, but it performs worse than functional approximation because it needs better tuning of hyperparameters and reward structure. Here's the second graph showing the percentage of runs that reach a platform before clearing room 1. Tabular Q learning learns too slowly and never succeeds within our time limit, while functional approximation progresses much faster.
This project explored the learning ability of tabular Q learning, functional approximation, and deep Q networks of passing rooms in Chapter 1 of Celeste. Functional approximation and DQN were both able to pass the first 3 rooms, but functional approximation did so for a far higher percentage of seeds than the first 1,000 deaths. This project is limited in how it holds actions for 15 frames to limit the state space, and the nature of Celeste, restarting at the beginning of the room, not the entire level, limited the testing of a model's ability to continue to pass room 1 after passing later rooms. Future work could involve more rigorous testing regarding that issue, as well as a relaxation of the constraint to hold actions for 15 seconds. It would also be interesting to explore performance on more complex chapters later in the game.